So in this video, we talk about the algebraic properties of inverses. This video is pretty quickly, but there is one small result where I once again really need to show it to you why it's true. Otherwise, it's going to be kind of amazing. So here are all the algebraic properties of the inverse. So if you have that A and B are same size invertible matrices, so they both have inverses, and K is a non-zero scalar, then if you take the inverse of the inverse, that's what this says, you get the original matrix. If you take A and transpose and take its inverse, it's the same as take its inverse and then take its transpose. If you take a power of a matrix and then take its inverse, that's the same as taking the inverse of the matrix and then taking it to a power. If you take a scalar multiple of the matrix and take it to its inverse, it's the multiplicative inverse of the scalar times the inverse of the matrix. So the scalar here, the power here kind of distributes through. The last one's the confusing one that really deserves an explanation. If you take a product of these two matrices and take its inverse, the result is the inverse of the two matrices, but the product is now in opposite order. It's now in opposite order. These results can be said verbally this way. The first one says the inverse of a matrix is invertible. It just so happens to be that that inverse is the matrix. The second one says the transpose of an invertible matrix is actually invertible, and it's the transpose of the inverse. So we normally say the transpose of an inverse is the inverse of the transpose. Okay, so the next one says the power of an invertible matrix is invertible. We also say it long form as the power of an inverse is an inverse of the power. The next one is the scalar multiple of a matrix, of an invertible matrix, is invertible. And the most important one that you'll hear me say by far the most is the product of two invertible matrices is invertible. It just so happens that the inverse is the product of those inverse matrices in the opposite order. Now, most of these are not difficult at all to prove, and you'll have one or two proofs to do in the homework, like the ones you've seen me do so far. They're like, you just kind of drag statements around. But I need to show you at least one, I think. The last one is by far the one people get confused by, because you think of -1 as a power, and you think, let's distribute that power, and that's just not true. Remember, matrix multiplication is not commutative. You can't just flip things. So in this case, that it does get flipped, the order is changed, is interesting. So I'm going to show you why it's true. It's not difficult at all. It's literally just a matter of just checking the definition. I'm claiming that the matrix A times B has an inverse. To check that this matrix A times B has that as its inverse, all we got to do is to take the matrix, multiply to its supposed inverse in both orders, and show you get the identity. So let's just do that real quick. If you have A times B inverse times A inverse, by associativity, I can associate that any way I want. Just don't change the order of the multiplication. That would then be A times B inverse times A, but that is, times A inverse, but that's A times I times A inverse. That is A times A inverse, and that's just I. So that's the identity matrix. So then, at least in that order, you get the identity matrix. I will leave the other half of the proof where you reverse these matrices and just do the product to show you that, yeah, indeed, that's right. They are actually inverses. Now, because of that, because of those properties, at least the power one, we can now define what we mean by A to a negative power. Before, we can only do it A to the positive integer power. So if you take A to a negative integer power, you really mean this multiplication. So A to the -2 power really means take the inverse of the matrix first and then square it. It just so happens, though, because the properties that I showed you, that this expression is the same as that expression. So you can think of it two ways. If you want to take A to the -2 power, you can first take the inverse and then square it, or you can square the matrix and then find the inverse. In the end, you get the same answer because of the algebra. Now, with that much, you should now be able to look at expressions like this and be able to solve for X. So assume that all these matrices here are all the exact same size. Assume they're all invertible, or else I can't write this notation down. So I want to go and show you what would X equal. We have to be really careful. For example, see this power? You can't distribute that power through because that's one of the properties of exponents that we do not have in general. So the right-hand side is really A inverse times B cubed times A inverse times B cubed, and that's the best we can do. We can't collapse that because we don't know if we can change the order of the symbols. But then notice on the equation, see how I could take A times A inverse times BX inverse, and that would have to equal to A times A inverse times B cubed times A inverse times B cubed. But then by reassociating, the A times the A inverse, this would be the identity. A times A inverse, that would be identity. You'll be left with B times X inverse is equal to B cubed times A inverse times B cubed. But then on the left-hand side, B and X are assumed to be in this right now. They're assumed to be invertible matrices. So the product of invertible matrices is invertible, and that becomes then X inverse times B inverse, and that would equal then B cubed times A inverse times B cubed. Well, that would then mean there's a bunch of ways to handle the problem now. I'm going to choose this way. I'm going to multiply both sides by X on both sides. When you do that, X times X inverse on the left would just give you B inverse. You then have to multiply on the left here to get X times B cubed A inverse B cubed. Okay, so then now I would divide by B cubed, but you can't divide by B cubed. You multiply by B to the negative third power. So I'd have B to the negative 1 times B to the negative third power. That would then equal to X times B cubed times A to the negative 1. And then I'd have B cubed times B to the negative 0, negative 3. Those cancel because they're defined to be inverses. So you just get that. Then I would multiply both sides on the right by A. Well, now, but this though, I can collapse that. Normal those laws of exponents still work because that's how we define the exponents. So that would then give you B to the negative 4. And then you would have X times B cubed times A to the negative 1. I multiply on the right both sides by A to get B to the negative 4 times A equals X times B cubed. You then have A inverse times A. That's the identity matrix. I won't put it down. And again, I'll multiply both sides by B to the negative 3 to get B to the negative 4 times A times B to the negative 3. You can't combine those because we're doing it on the right. And that would then equal X times B to the third times B to the negative 3. Think it as B to the 0. That's the identity matrix. So that's just X. That's the answer. That's what X equals. So if I knew more about what B and A are and how they relate to each other, if they happened, if B and A actually commuted, then I could actually do more algebra. But unfortunately, I can't. And I believe that's enough for that video.